Welcome everybody back from spring break. Today we're going to do day 10-7 projectile motion. Just as a side note, this is a CNC machine. You program this on a computer and then this moves around and cuts a piece of wood. It's one of the tools in my workshop. So let's play. So projectile motion, if you are in or have been in physics, today should be very comfortable, but I am going to teach it as if you don't know any physics. Now, the warm-up is review. So it says determine simultaneous or non-simultaneous. Technically, this should say or/and, depending on whether or not we have any. Find the TXY for simultaneous and the XY for non-simultaneous. So the first thing that we will do is find simultaneous. So simultaneous, we can set x equal to x or y equal to y. Not that solving the quadratic is difficult, but if I have the choice between linear and linear or quadratic and linear, I'm going to choose the linear and linear. So 2t minus 2 equals t plus 2. So then t equals 4. So that means x is the same when t is 4. x1 would be 8 minus 2 is 6, and x sub 2 is 4 plus 2 is 6. So that checks out. We probably don't have a calculation mistake there. So now there's a couple different things we can do. We can set y equal to y and solve, or we can take the value that we got for when x is the same and sub it into both. That's probably easier in this case, so I'm going to do that. If I sub 4 in, I get 8 plus 3 is 11. And y sub 2 would be, what are we squaring? 16 minus 5 is also 11. Well, x's are the same, y's are the same when t is 4. So that means we have a simultaneous solution at the point 611 when t equals 4. All right, now we got to try to find non-simultaneous solutions. So for non-simultaneous solutions, what we do is we eliminate the parameter here, we eliminate the parameter here, and then what we do is we make a system out of those two values, or those two equations. So if I eliminate this parameter, I'm going to solve for x. So solve for t. So that would be x plus 2 over 2. If I sub that in for y, y would be 2 times x plus 2 over 2 plus 3. The 2's cancel, and we get x plus 5. So x plus 5 would be the rectangular graph that matches with this parametric equation. Do the same thing with this one. So t equals x minus 2. So y equals x minus 2 squared minus 5. Sorry for the lighting. I'm trying to see if I can get this lit better, but it's coming from the side, so that it's causing a shadow. By the end of this thing, I'll be a ninja at lighting. So now we create a system. That was horrible. With y equals x plus 5 and y equals x minus 2 squared minus 5. So with that, we can solve using any of the methods we've had. Without a calculator, I think substitution is probably going to be the easiest. So x plus 5 equals, I'm going to square this out, x squared minus 4x plus 4 minus 5. So bring everything over to one side. 0 equals x squared minus 5x. That's minus 1 minus another 5 is minus 6. So now I'll come up here. That factors into x minus 6, x plus 1. So x equals 6 and x equals negative 1. Now the x equals 6 we already have as a simultaneous solution, so we don't have to worry about that as a non-simultaneous. If it is simultaneous, we ignore it as far as the possibility for a non-simultaneous. So now what we do is x equals negative 1. So when x equals negative 1, we come back to either of these two equations and sub it in. Y would be 4. And just for confirmation that we didn't do something silly, let's see here. Negative 1, that'd be negative 3 squared is 9, minus 5 is also 4. So that means we have a non-simultaneous at the point negative 1, 4. And again, we don't include time because time is not when these cross, or at least there's two different times when they're both at this point. So I'll pause just so the videos aren't very long, and then we'll try number 2. Number 2 says, given the parametric equation x equals sine squared of t and y equals cosine of 2t for all t, eliminate the parameter to write the rectangular coordinate equation. All right, so let's see here. There's a couple different things to notice. I've got a sine and a cosine. That's an issue. I've got a squared. There's something that isn't squared over here. And I've got 2t, but over here I have t. So all of those are things we might need to deal with at some point. I think the most critical is the 2t, because I can square both sides of this one and get them where they're both squared, or I can write this as 1 minus cosine squared and get them both to be cosine. But that 2, there's really nothing I can do other than using a trig identity. So the trig identities we had for cosine of 2t, there were 3 of them. We had cosine squared t minus sine squared t. That one's not very useful because I would have both functions there. And then another one was 2 cosine squared t minus 1. Now that one's not bad because it's only got 1, but I would really rather have sine squared so that I could swap it out with an x. And that works out that that's the third one, minus 1 minus 2 sine squared t. So I'm going to rewrite y as 1 minus 2 sine squared t. So sine squared t, all of this, I can just replace with x. Y equals 1 minus 2x. So if I graph these, they are going to live on this linear equation.
Oppan Gangnam Style.
All right, so on the back, we have projectile motion. It says the acceleration of an object due to gravity on Earth is roughly 9.8 meters per second squared, which means you gain 9.8 meters per second, or 32 feet per second squared, which means if you're in feet, you gain 32 feet per second. Because the derivative, new word, of distance or displacement, no, it's distance, is velocity, we use 4.9 for meters. Explanation to come in about 200 days. So this is a very common thing, an interaction that you will do in calculus, but for today I'm just going to kind of hand you equations that you will derive once you get into calculus. We just don't have the info in our heads yet to do that. So Phil hits a pitch which is waist high, 1 meter above the ground, with an initial velocity of 36 meters per second at an upward angle up from sideways of 38 degrees. The ball is hit towards Power Alley in left center field. So if you have a baseball diamond, like this is a top view, where you've got the bases here. Power Alley is about here. Just vocab that's kind of interesting. And that fence is 125 meters from home plate and is 4 meters high. So this view is kind of hard to get heights into it. So what I'm going to do is I'm going to draw it horizontally. So it says explain in words. I'm going to do it verbally, but while I draw a picture. So the ball starts 1 meter high and it's traveling at an initial velocity of 36 feet per second, meters per second, at an angle of 38 degrees. It's going to go like this, and then somewhere over here, actually not somewhere, 125 meters away, there's a wall that is 4 meters high. It says the center fielder can jump and catch any ball which is less than 3 meters high. So assuming that the center fielder is here, they can jump and get to a ball that is 3 meters high. So there's 3 possibilities. Either this ball goes over the wall, it goes lower than 3 feet and gets caught, or it hits right in that gap and then it would, I guess, bounce off the wall but not be caught. So what are we going to do this? Well, first thing is we're going to break this velocity up into its components. And those components would be magnitude cosine 38 degrees, magnitude sine 38 degrees. That should look familiar. We did that last unit. So the equations to model anything being pulled on by gravity on Earth look like this. The y is negative 4.9 t squared, because the y is quadratic. It's going to go up and then come back down, plus the initial velocity in the y direction times t. Well, that's the initial velocity in the y direction. That's going to go in there, plus the initial height. Well, the initial height is 1. The other equation, and that 4.9 is a constant. That is a constant if we're in meters. If we were in feet, we would use the 16 because it's half of the acceleration of gravity. You'll learn that next year. X is just linear. Like if we looked at a shadow as this moved, the ball would just horizontally travel along the ground, or the shadow would, at a constant rate. We take our initial velocity in the x direction, and we just multiply it by t. Now, there is technically a plus horizontal, like, initial position, but for this one, I'm going to call this spot right here the origin, so that this is plus 0. But there is the possibility that that would be something other than plus 0. So, write parametric equations. I always start with x. X equals 36 cosine 38. Oops, sorry. In the equation 1, this should be velocity initial in the x direction, t. I'd already kind of subbed this in, t. And y equals negative 4.9 t squared plus 36 sine 38t plus 1, because that's the initial height. And then the third question is kind of open-ended. What happened? So what we need to do is figure out, did the ball go over, did the ball get caught, or did the ball hit the wall in between the glove and the top of the wall? So with questions like this, you will almost be guaranteed that you will have access to a calculator. So let's go to our calculator. So if I turn on my calculator, if I'm in the home screen, let's see how to start here. So the first thing I'm going to do is I want to watch the path of the ball. So I'm going to go into mode. I'm going to make sure I'm in parametric, and because the degrees for the angles were in degrees, make sure you're in degrees here. Press Y equals, and at that point I'd type in everything. I pre-slotted it just to save us some time. If you need to type those in, pause the video. I'm going to go into my window. So time, -2, it probably doesn't take more than 5 seconds for it to get to the wall. So I'm going to leave that at 5. The T step, if it's too fast, like if the ball just, and we can't really tell what happened, make that smaller. If it's too slow, make that bigger. X is our horizontal distance, so I'm going to go -1, and then we actually want to know when it hits 125. So I'm going to go to 130 for max. And then for Y, I'm not really sure what would be a good Y max. It's kind of a guessing game. I'm going to leave 130 for now and see what happens. So let's go back into Y equals. Now, one thing I would suggest is it makes it a lot easier to see what happens if out front you have that dash with the circle in it. So let's graph and see what happens. And there's the ball. All right, so it hits over here. It does that path. It looks just like we had here, more or less. So that's more of a check, just do we have something weird? Like I was originally, when I did this question first, I wasn't in degrees, and the ball just went bloop, and I was like, oh, there's something wrong there. So now, how do we determine whether the ball made it out of the park or not? So here's what we're going to do. We go back into function, go into Y equals, and then we want two functions. We want to know, when does this X equation get to 125? So all I'm going to do is I'm going to type in the X equation. Now the variables get kind of weird because instead of X and T, it's Y and X because the calculator only has inputs and outputs. And then for the other output, I want 125. I turned this equation off. I'm going to need that later, and I just pre-typed it in. So I'm going to go into my window, and again, I got to remember, X is now time. So 130 for time is weird. I'm going to go to 5. It worked last time. And then for the y values, those are the x values in my equation, and -5 to 130 works. So press graph. So here's the wall, and here's the distance the ball has traveled horizontally, and they look like they're going to collide right there. So when I solve this, I'm going to get a t value, because this is the t-axis right now. Second, trace 5, enter, enter, and there's only one intersection, so for the guess, I can just leave it empty and press enter. So that means, so ball goes 125 meters horizontally when t equals 4.406 seconds. All right, so now what we got to do is say when time is 4.406 seconds, what's the height? Because that'll tell us whether when it gets here, is it too high, right in the middle, or low. So I'm going to go back into y equals. I'm going to turn off both of these equations. You could just delete them and retype type the other equation. I just was trying to save time. Go into the window. So x is t, that works. And now y is the y, because we're actually using the y output. And these bounds, I think, worked pretty well for the other one. I'm going to press graph. So this is now t versus y. So I want to know when t is 4.406. So there's several different ways you could do this. Once we have the graph, I think one of the easiest ways is press second trace and go to value, and it asks for an x value. Type in 4.406, and the height of the ball, let me write this out. Ball goes 120 and 4 points, and at that time, x is actually, y is 3.531 meters. So to summarize, the ball will be at a height above the glove, but below the wall top. It hits the wall. All right, so that is how we do a problem with projectiles. If we just kind of run through it, we break the initial situation up into components. We write equations based on these two formulas. We then will have either a constraint in the x or the y. For this, we had a constraint in the x. We want to know when it goes 125 meters. We determine what t values it has that horizontal distance. We use that t in the other equation to determine, in this case, the height. If we were given a certain height, let's say a window is a certain height, what would be the horizontal distance to make it go in the window? Well, that would change the order in which we do it. We set y equal to the height, find t's, and then sub that back into the x's. All right, so would you please try number 3? There'll be a key for this worksheet on Canvas. If you have any questions, come into office hours. As usual, it'll be the last 15 minutes or so of each period.
오빤 강남스타일